Hey, what's up, you guys? So, in our previous videos, we covered questions 1 through 5. And in this video, we'll proceed with question number 6. So, basically, this one right here. Okay. Now, again, before we dive into the solution, let's quickly revisit the steps. Okay. So our first step was to substitute our power series representation y prime, and y double prime into our differential equation. Then we match the exponents or the powers of x to n so that our x has the power n. Then we shift the indices so that all the series start from the same index. Okay, so we will have multiple series and all of those series may or may not start from the same number. So if they do, amazing, we don't have to do anything. But if they don't, then we kind of have to shift one or two of the power series. But which one do we shift? We always shift the lowest ones, the lower ones, okay? And we keep the larger indexes. Okay, and then once we're done with our second and our third step, then we can combine our series to 1, okay? And then our fifth step, then we find our coefficients for a sub n using recurrence relationship. And then right after we have our coefficients, we can then find our general solution, which will be in this form. Okay, so let's get started with our question. So today we have y double prime plus xy prime plus xy equals 0. Again, this is our homogeneous differential equation because our right-hand side is a 0. So let's perform our first step, which is substituting our power series representation into our main differential equation. Okay, so we have our y, which is summation from n equal to 0 to infinity, a sub n x to the power n. And this goes, we all know, under a red box. Then we have our y prime. So again, since we are doing our first derivation, that means our index increases by 1 to infinity a sub n times x to the power n minus 1. And our y prime gets a green box. Okay. And then we have our y double prime. So now again, our starting index increases by 1. So now it's 2 to infinity a sub n times n minus 1 x to the power n minus 2. And we know that this one gets our blue box. Okay, so these are our power series representation, right? And now we are going to substitute that in our main equation. Okay, so first we have our y double prime. So let's write that. Infinity a sub n times n minus 1 x to the power n minus 2. Then I have my plus, and then there's an x. And then I have my y prime. So we have from 1 to infinity a sub n times x to the power n minus 1. So bracket, and then our x again. Then we have our y, which is 0 to infinity a sub n x to the power n, then 0. Okay. Right, so let's now distribute our x to their respective power series. So I have summation n equal to infinity a sub n times n minus 1 x to the power n minus 2. Then we have our plus. So now it gets distributed. So I have from n equal to 1 to infinity a sub n times n times x to the power n. Because again, by rules of exponents, right, if our bases are the same, that means their powers adds up, right? And for one x, I have the power n minus 1, and for the other x, I have a power 1. So when I add them up, I'm left with just an n. Okay. And then I have my second x, again, gets distributed with my third power series. So then I have a sub n x to the power n plus 1. Because, again, by rules of exponents, our bases are the same. That means their exponents adds up. So one of our x's has the power 1. The other one has the power n. So if we add them up, we are left with n plus 1 equals 0. Okay? So this is how our first step, after completing our first step, looks like. So now we are moving on to our second step, which is to make sure that these powers of x are all n's. And as we can see that our second power series already has the power n attached to its x. So that means the second one doesn't need to be transformed. So we only need to transform the first power series and the third power series. Okay, so let's go ahead and do that. So I have my first power series to infinity a sub n times n minus 1 x to the power n minus 2. Now it's going to be transformed so that its power is just an n. And okay, I'm going to use my blue color again. For some reason, I love this color. Okay. Okay. That looks good. All right. So first we had on our left, we have our n minus 2, and we know that our powers needs to be just an n. So if you observe clearly, if we just add a 2 to it, that means the negative 2 and the positive 2 gets canceled. So I'm just left with an n. Okay. So that means all my n's, so this n, and this n, also gets added by 2. Okay. So if we do that, then we have a sub n plus 2 times n plus 2 times n plus 1. Okay. And now since our all of our n's increased by 2, that means my starting index, you'll already know, decreases by 2. So it's going to start from 0. Okay, so that is my transformation of my first power series. Now let's transform our second power series. My third power series. Again, we're not doing our second power series because it's already, the power is already an n. So we don't have to do anything with that. Okay, a sub n x to the power n plus 1. So now, again, it gets transformed. I'm going to select another color. Let's pick an orange. I don't know if it's an orange. Okay, I'll pick this color. So I have the power n plus 1, but I know that I need to transform this so that its power is also an n. So if you look clearly, all we got to do is subtract 1 from our power, from our existing power. And if I do that, that means all my n's also decreases by 1. So that means my a sub 1 is now a sub n minus 1. Okay. So now since our n's decreased by 1, that means my starting index increases by 1. Okay. So this is how our transformed power series looks like. So let's now rewrite that so that now we have our new transformed power series. Okay. So, right. So my new transformed power series, my first one, starts from 0 to infinity, a sub n plus 2 times n plus 2 times n plus 1, x to the power n. And then I have my plus, and then like I said, my second one remains as it is. Okay, n times x to the power n. And then I have my plus, and then now I have my third transformed power series, which starts from 1 to infinity, a sub n minus 1 times x to the power n equals 0. Okay? So as you can see, this is how our differential equation looks like right after we have completed our second step, which was making sure that all my powers of x are n. Okay? So now my third step is to make sure that all of them start from the same index. Okay? So that means this one, and this one right here, they all are the same number. Now, which one do I pick, right? Like, which one do I shift? So again, like I said previously, that we would always want to keep the power series with a larger index and shift the power series with a smaller index, okay? So that it gets transformed or it gets shifted to a larger index number. So as I can see that both of my second and my third power series, both of them, their indexes start from 1, okay? But our first one, our first power series, the index starts from 0. So now I want to shift it so that it also starts from 1, okay? So again, we can definitely do that. All we gotta do is write the n equal to 0 terms separately, okay? So now if I do that, then I have a sub 0 plus 2 times 0 plus 2 times 0 plus 1 times x to the power 0, which basically is 2a sub 2. Okay, so let's write all of that. So now I have 2a sub 2 plus, and then now I can write my first power series, and so now it can start from 1. Okay, then I have my plus, then there's our second power series. Then I have my third power series, again pulling up the green color. Okay. It's a little lighter color as previous one, but it's fine. We can still work with that. Equals 0. All right, so now I can see that both my powers of my x and my starting index, they're all the same. So that means I can now perform my fourth step, which was combining all these three series to 1. So let's go ahead and do that. So I have 2a sub 2 plus summation n equal to 1 to infinity. We have our x to the power n as common. So let's pull that out and then write the leftover terms. Plus a sub n plus a sub n minus 1 equals 0. Okay, so this is how our differential equation looks like so far. Okay, so we have done our fourth step. Now is the time to determine our coefficients, right? So these ones right here. Okay, so for that, like I said, the first thing we do is we look and compare what we have on our right. Okay, so we can see that on our left we have a constant number, that is 2a sub 2. Okay, and I can say that it's constant because there's no x attached to it, right? And now if I look at my right, I can see that clearly it's a 0. That means our constant is equal 0, okay? Which basically that means that our a sub 2 equals 0, okay? Now we have our a sub 2, but if there's an a sub 2, clearly there is an a sub 0 and there's a sub 1, right? And we know that it's a second order differential equation. That means I'll have two arbitrary numbers. So I can say that our a sub 0 and our a sub 1, both of them are arbitrary. Because again, we are not given any initial values, right? Okay. Now I have the second part of the differential equation, which is this power series part. And I can see that this is valid when my power begins from 1. So basically all of these are my coefficients now because there's an x attached to it. So just by looking at my right, I can see that all my coefficients will be a 0. So let's write that. Okay, so I have this, and now I want to isolate my a sub n plus 2 to find my recurrence relationship. Okay, so this is my recurrence relationship for and this is also, let's not forget, it's for n equals to greater than or equal to 1. Okay, so this is how my recurrence relation looks like. Now, according to my question, I'm supposed to generate some terms from my recurrence relationship. So let's go ahead and do that. So we know that our n starts from 1. So let's plug in those values. So I have equals 1. I have a sub 1 plus 2, which is a sub 3. And then I have negative a sub 1 times 1, which is just 1. And then I have negative a sub 1 minus 1, which is a 0, divide by 1 plus 2 times 1 plus 2 times 1 plus 1. Okay, so that gives me negative a sub 0 minus a sub 1 divided by 6. Okay, so that is my a sub 3. Okay, then similarly, let's do for n equal to 2. Then I have a sub 2 plus 2, which is a sub 4, equals, we'll need that, I have negative 2 times a sub 2 minus a sub 2 minus 1, which is a 1. Then I have 2 plus 2 times 2 plus 1. Now, if I look at our a sub 2, remember it's equals 0. That means my first term is 0. And then I have my a sub 1, which I already said it's an arbitrary number. So my numerator is just negative a sub 1. And then my denominator, 2 plus 2 gives me a 4. And then 2 plus 1 gives me a 3. And 4 times 3 is a 12. Okay, so this is my a sub 4. Okay, all right. Then let's do n equals to 3. So I have a sub 3 plus 2, which is a sub 5, equals negative 3 a sub 3 minus a sub 2, divide by 3 plus 2 times 3 plus 1. Okay, so again, my a sub 2 is a 0, so I'm just left with negative 3 a sub 3. So we can write our numerator as negative a sub 0 minus a sub 1 divided by 6. And then in our denominator, we have 3 plus 2, which is a 5, and then 3 plus 1, which is a 4. So 5 times 4 is a 20, which is our A5, and this 2 gets a box. Okay. So now in our question, it asked for 5 terms. So I think we are done with our 5 terms. So let's write our solution. So I have my a sub 0. Oops. Okay. Sub 0. That is an arbitrary number. And then I have my a sub 1x, again, my arbitrary. Then I have my a sub 2, like we've seen, is a 0. Then I have my a sub 3 right over here. Negative a sub 0 minus a sub 1 divided by 6, x to the power 3. Then I have my a sub 4, which is negative a sub 1 divided by 12 times x to the power 4. And then I have my a sub 5, which is 3 divided by 20. And then negative a sub 0 minus a sub 1 divided by 6 times x to the power 5, and so on. Yeah, so there are like 5 terms, just like our question asked. Now, again, this is that condition where this is like you're in a situation where you can leave this answer as it is, or you could also further simplify it. There are people who might want to get rid of this negative so that, all my a sub 0 and my a sub 1 just becomes a positive. So I have a minus sign by right. And then you can also simplify this one right here, canceling my 3 and 6, and then multiply 20 times 2, which turns out to be 40 in my denominator. So again, simplification, there is no correct way of simplifying it. You can simplify as many ways as you want, but I'll just leave the answer here as it is, okay? So this is my solution for question number 6, okay? Now, hope this helps, and I hope you enjoyed watching this video as much as I enjoyed making it, and I will see you in my next video. Bye!